So Guillaume Bichot from Broadpeak. I'm the head of a team called Exploration, so basically we explore. So we take stuff from the features and new stuff that we can find, and we try, we experiment it, and possibly we integrate it in our product if it makes sense, right, basically. So today I'm going to talk about a server-side adaptive bitrate streaming technology. So let's start with a bit of background. You know how ABR works, basically. You have a content that is encoding in several flavors, several representations. And all these representations have different encoding bit rates, different qualities, and they are all, split in segments of equal duration, let's say 2 seconds. And then you have the player on the bottom that, requests segment after segment. And it can switch from one quality to another quality based on this bandwidth estimation, the maximum available bandwidth on the link between itself and the server. And it can also look in this buffer, the buffer occupancy. In, let's say, server-side adaptive streaming, so I call it S4S. In short, it means server-side segment selection for streaming, S4S. It's quicker to say S4S. So with this technique, the bandwidth estimation is done on the server side. That's it. So whatever the player, and we are going to see what does it mean exactly, whatever the player is requesting in terms of representation, in terms of quality, the server decides and will return whatever is his choice, right? The use case that I'm going to talk here is low latency. So we have an issue with low latency. The player basically is not capable of estimating correctly the maximum available bandwidth. Why? Because in low latency, a segment, the time to transmit a segment is roughly equivalent to the duration of that segment, roughly 2 seconds in my example. So if the player use the common and classical way to estimate the bandwidth, roughly he will estimate the video encoding bit rates, right? Doesn't work. It won't estimate the maximum available bandwidth over the link. So this is the issue. We don't have this issue with the server side. Why? Because we do not rely on HTTP for estimating the bandwidth. We rely on the underlayer, the transport layer, and even more precisely, we rely on the congestion control ability to estimate the bandwidth, right? Yeah. So we have basically 2 modes for operating this server-side adaptive streamings. The first one is called transparent. That means it's transparent for the player. What we do is that we prepend the initialization segments to the media segment systematically for all segments, in such a way that if the player requests a particular representation, a particular quality, maybe the server will serve something else. It will serve the segment, but in another quality. So in order to avoid problems in the decoder sides, we prepend the right init segment. It's called a self-initialized segment, and the player doesn't know exactly what's going on. It doesn't receive exactly the quality that he asked for, so not exactly the same bit rate then. But anyway, its objective is to feed the decoder as soon as possible, right? So it works. The second mode is what we call the non-transparent mode. So here we have a specification, we have a protocol basically. It's a protocol, and we're going to publish soon this protocol. It will be available for everybody that wants to experiment and implement such a mechanism. So it's a very basic protocol, either based on HTTP custom header or based on query string parameters. The players request some things, like it's completely compatible with the adaptive streaming basic protocol, right? The player requests a segment and the server responds. But when the player requests a segment, he can join in the request the list of the available qualities, available representation. It avoids the servers to be aware of all this stuff. It doesn't need to, browse the manifest or whatever. It's completely stateless for him. And the server will select a quality among those provided by the player, and he will send in his response, he will tell to the player, hey, this is the one I've selected. Very basic protocol, right? The player can has the opportunity to also join information about how much the backgrounds use in terms of bit rates, in terms of bandwidth. Backgrounds represent the audio, subtitling, whatever consumes some bandwidth, some extra bandwidth, right? The player has a possibility to indicate the path of the initialization segment. If it does that, then the server can respond can return a self-initializing segment, right? It may be also convenient for the player. It doesn't need to mangle. It doesn't need to manage anymore this initialization segment, right? But maybe the player doesn't want to handle this because it doesn't support that. So it's just an option. It doesn't need to join and to indicate the initialization path. In that case, it will manage the initialization segments like it used to do, right? Conventionally, I would say. In the same time, we have a protocol. Now we can join more information. We can attach more information. So, for example, the player can indicate what's the buffer occupancy, how many, for example, stalls he has experimented, and the server can indicate this bandwidth, raw bandwidth estimation it does with the previous request. Such kind of information, right? So all this stuff, I'm going back to this, but all this protocol has been and is currently encapsulated, if you can say that, encapsulated in a CTA protocol called CMCD, if you have heard about that, right? CMSD is also a protocol that yet to be published, but it's going to be published soon. And these are protocols to exchange informations, between the player and the server. So this S4S protocol has been encapsulated and is currently under the encapsulation process, right? It will be part of the spec that we're going to publish. So the heart of the subject today is to say, well, okay, we need to test it, right? So in a conference, system conference, MMSys in 2020, Twitch has managed the challenge. In this conference, each year, you have a kind of grand challenge organized by one company. It was Twitch at that period. And this guy decided to organize a challenge around algorithms to solve the low latency problem I mentioned earlier. So there have been a winner, L2A, LL. So the winner at that period was the two first algorithms. The first one was based on online learning, and the second one was based on LOL, was based on how to isolate traffic burst, in order to be capable of, computing bandwidth estimation that makes sense, a maximum available bandwidth that makes sense. So what was this grand challenge? During this grand challenge, Twitch published in an open source way, published frameworks to implement in order to test these algorithms. So they were client-side algorithms. So we discovered this too late, so we could not participate. And anyway, because it's server-side, it would have been changed a lot, the framework, and you're going to see why in a further slides. So the original framework was this one. You had a player on the top. The player gets segments from a streaming server, an open source one, from the same team than FFmpeg, by the way. Then an encoder, FFmpeg, and the encoder, launch of the encoder, and the control of the bandwidth variation was done by a script called Test Runner, provided by Twitch. And these tools, script were using dev tools in order to make variation, in the bandwidth. So then they published the results, they published also the way to compare the things. So basically, they have a notion of profile. There were 5 profiles, cascade, they changed the bandwidth by steps, like that. Intra-cascade, you had more steps and so on. Spike, very spiky change of the bandwidth, very quick change of the bandwidth. Duration, average bit rate that was expected, number of switches that was expected, and so on. And then they computed a theoretical target, right? Average bit rate 678. If you correctly, managed all these profiles, you should exhibit an average bit rate of 678 kilobits per second, right? 0 second of duration, 1 second of latency, and so on. And then they did the test for the -JS, the default algorithm. And they found the result. As you can see, 276 kilobits per second, more or less, the default algorithm stick to the lowest layer and doesn't move a lot. It tries to move sometimes, but basically stick to the lowest layer. So not good for us. We want, adaptation, right? Basically, what they do, they published the result through a video on YouTube, explaining how they computed the result, and they, according to their result, you can see L2A. They compare the result regarding the advantages, or let's say the addition or the subtraction of the comparing with the default algorithms in -JS. So here for L2A, you can see that there has been 60% of improvement in terms of average bit rate. That's the main target, right? So they did that. They did the same for LOL, right? Again, and they published their result. That's it. So what we did. We took this same framework, and then, of course, we updated it in order to be capable of testing, again, LOL and the two winners, LOL and L2A, LL, but with our algorithm, server-side algorithm. So what we did, first of all, we updated and upgraded the Dash player. The version was, we did that last year, so end of last year, so the Dash version, the player increased in terms of quality. So we took the last version we have. We put our streaming server as a proxy between the streaming server and the player. We inserted our server as a streaming proxy. So basically, when the S4S function was not enabled, it was just acting as a proxy, forwarding the request, forwarding back the response from the server. And then instead of, on the test runner side, instead of using the dev tool, we use a real traffic shaper because we had problem with this dev tool. Shaping the bandwidth on the HTTP level doesn't work with our server, especially because we are working on the TCP level and not on the HTTP level. A real traffic shaper based on TC, Linux TC. And and the last thing that we do is we review the parameters of the encoder because there were some bias in the encoder, the way it's been configured. You had, especially in lowest quality, you had some peaks like that. It was very damageable for the test. So anyway, we also adapted the players to support S4S, Yeah, so and then we developed a specific page also to follow what was going on with that new server-side algorithms. And then we retested the basic algorithms, the first one, the winners. We just detected, just to see that the baseline changed completely. We had the latency that was reduced very significantly. That was mostly due to the fact that we changed the encoding parameters that was not really correct in the Twitch experiment. Anyway, we restart all the test sequences like Twitch did at that period. So basically, the condition of test was the following: free representation, very small bit rates, 200 kilobits per second, 1 megabits per second. As I said, we changed the FFmpeg parameters in order to be more CBR, a little bit more CBR friendly than it used to be. We added a new test sequence based on doubling the bit rates because in our kind of business, it doesn't mean anything to manage such kind of bit rates. We need to have more substantial bits over the line. We keep the target latency 1 second. Segment duration of 0.5 seconds is very small, right? It was a choice from Twitch, but we made also some tests with 1 second and 2 seconds segments, which in terms of quality is something more reasonable, I would say. We keep the CMAF chunks. So yeah, remember, I assume that you know that, but in low latency, we take the segment, and the segment is split in chunks that are sent, on the fly directly from the encoder. They crosses all the elements over the network up to the player, right? So then, if something is buffered at some time, it's just this chunk, never the segment, just the chunk. So the chunk here, the duration of a chunk is basically a frame, a video frame. And then we run the test procedure exactly like Twitch did, 5 runs for each of the network profile I mentioned earlier. And we averaged the result over the 25 tests, right? So then this is the result. Well, at least an extract of the results. So remember, the target, the main target is this average bit rate. So you can see that S4S. So the theoretical target was 678 for the entire set of tests. And you can see that S4S got it, right? Reached it. Stock means the basic algorithm, right? So it's right below, LOL is below, and L2A is always over the limit, which means it stucks. On the right side, upper right, you have the stall duration, so L2A, stalls a lot because it's too optimistic, right? S4S has a decent stall duration. Again, the target is exactly reached. You can see the number of switches. So in theory, 5 switch. So S4S is a little bit over the maximum, over the theoretical target, especially for the 0.5 segment size, which doesn't mean a lot for us, right? Okay, so very good test. We double the bit rates, and we have same kind of result. You can see that S4S is right on the target. The target was 1,357 bits per second, and we are right in there. Again, for the others, roughly the same result than before, right? Number of switches, a bit over switch, for the S4S. Nothing is perfect, right? Yeah, so we have a lot of other intermediate testing where we show, with different profiles and so on. So you can go to the site. We have published on our blog the other results that you can access, right? The last test I wanted to share with you is about the QE. There was in the Twitch Grand Challenge, they gave to us a kind of aggregation formula where they aggregated all the QE metrics in order to publish an estimation, a QE, overall QE estimation metric. What you can see is that the S4S, this is a yellow bar, is right ahead of regarding the others. This is true for the old profile, and this is, depending of the duration of the segment, but basically it's ahead also for the other type of profiles. So in conclusion, I compare this MMC's 2020, let's say, result with S4S. So what we did first is we retest LOL. By the way, we have used also a different version of LOL, something called LOL Plus, because it's been upgraded by the team that is behind this algorithm. So LOL Plus performs slightly better than it used to be with the MMC's Twitch challenge. L2A is still above the target, but with a very long stall duration. That's basically what we can say. And regarding S4 streaming, we have a bitrate target that is, a measure bitrate that is very close to the theoretical target, right? For a decent stall duration, as I said, and the best QE score. So then, S4S run first, for the moment at least. As I said, there is an article that you can read on our blog. So what's next? We have already started the next. So first of all, as I explained, we are in the process of encapsulating S4S in this protocol CTA 5004, which is again the protocol called CMCD. That is a set of parameters for the client, for the terminal to communicate to the server. So we're encapsulating our information, S4S information, in that protocol, and we're going to do the same with the other protocol called CMSD, not yet published, but it's going to be published soon, I guess. Same thing. We're going another test campaign with Fraunhofer Focus. This is ongoing. It's not, I would have loved to share with you the first result, but it's not yet ready, so we have to wait. We have a reference player that we are going to communicate and share with the -JS community. It will be a specific branch where you can get it and test on your side. And we're going, as I say, to publish the protocol, the S4 streaming protocol as well. That's it.